Good morning, this is Deep Generative Models. Today we are going to talk more about the generative adversarial networks. Specifically, we are going to talk about the L-scan, W-scan, and some metrics so that we can evaluate our generative models. So let's talk about the least square generative adversarial networks. The least square generative adversarial networks ask an interesting question. That is, do we have to use cross-entropy as our loss function to train our generative adversarial networks? And by the title, you can see that it suggests that by using the least square loss, which is the mean square error as our loss function, may be a good way. The loss function looks like this one. Instead of forcing the dx to be 1 when x is a real image and dgz to be 0 when gz is a fake image, it actually forces the dx to be b when x is from the dataset. That is when x is a real image, and dgz is going to be a. And instead of making the dx better when x is a real image, it actually forces the dx output to be b exactly, no more and no less. And the same thing happens to the case that when we take a fake image. And for the training of the generator, we are pushing the output of dgz to be c. So why not just fix that b equals to 1 and a equals to 0 and c equals to 1? This seems to be fine, right? Because we know that 1 means true, 1 means good, 0 means bad. Why not just use 1 and 0? The reason is that some set of ABC has better theoretical properties. So when ABC is equal to -1, 1, and 0, if we are using this loss function, just kind of like original gain. The original gain, when we train the original gain in the cross-entropy loss, in theory, generated distribution and the true distribution, the difference between them are minimized in the sense of minimizing the adjacent channel divergence. In this case, if we are using this loss and ABC equals to these numbers, -1, 1, and 0, then it turns out because we can actually, like the original version of gain, we can compute the optimal output of D. And we can actually see that this process is minimizing Pearson chi-square divergence, like the original game. Although this set of setting has some good theoretical properties, it is perfectly fine if you choose the more apparent value like b is equals to 1, c equals to 1, and a equals to 0. But theoretically, it suggests you to use this setting of values. There's a terminology called f divergence. F is any function. By given any function, we can define a divergence. This divergence is a measurement between two distributions. So actually you can, if you see our lecture notes, so you can see that in here. By trying to manipulate the loss functions, you can ask the game process to minimize different kind of divergence. Okay, so let's talk about the W gain or Western gain. So this one is a very interesting approach to what the gain is. Just like we mentioned before, there are many different ways to measure the differences between probability distributions like KL divergence, adjacent channel divergence, and there are also something like the Earth mover or Watson one distance and total variation. So what is a total variation? The definition seems a little bit complicated. That is, we find out event in the terminology. It calls an event. So that maximize the differences between these two probability distribution. That is, you find out one event. So the probability, if you compute the probability of this event in the first distribution, and you got a probability, and if you consider the second probability distribution, you can also compute the probability of that event, and you compute the difference between these two probabilities. So among all possible different events, you find the one event that maximizes the differences between these two probability distribution. So that is total variation. However, our main character here is the Western one distance, or the Earth mover. So what is it? Okay, so the Western distance by the definition is, okay, we have two probability distributions, PR and PG. So PR and PG, we just treat them as separately, but by consider them as a marginal probability distribution, we can consider the joint distribution of these two distributions. So what does it mean? Let me give you one example. So consider we have two distributions, and they all have 5 different outcomes. Let's say A, B, C, D, E, or 1, 2, 3, 4, 5, just five different outcomes. So this guy also have 5 different outcomes. 1, 2, 3, 4, 5, or A, B, C, D, E. So what does it mean by the joint distribution? You can consider the joint distribution as these gray boxes, So we have two distributions. One is the blue one, and the distribution, if you consider a graph of the distribution, it looks like this one, and the other one is the green one. It looks like the bottom one. Let me turn off my camera so you can see it more clearly. Okay, so we have these two distributions. So what is a joint distribution? The joint distribution is we need to fill out the number in this gray box. So the first one means the probability that you consider you have two outcomes. So the first outcome is A, and the second outcome is also A. You can see it. Let me use a laser point. Okay, so you can see right here, or maybe we should. So here, this one is AA, because suppose this one is A, and this one is A. So this one is A. We have two. So you may consider we have two dice. We throw the first one and get the first outcome, and throw the second one, get the second outcome. Only that these two dice may be correlated to each other, and the first dice, it only have 5 outcomes, and each one of have the probability like 20%, and the second one has a probability distribution like this one. So this one is AB. Maybe we should say BA, because if we put this one as the first one, so this one is the probability of this one is B, and this one is A, and this one is the probability that this one is C and A, and so on. So for example, this one, because this one is B, so this one is CB. So you get an idea that we actually have 5 times 5, 25 different events. Although some of the events is the probability 0, because all these guys should not actually happen. But theoretically, because our space is ABCDE times ABCDE, the product space of ABCD and ABCDE, so you should get like 25 different events. Okay, so you can see that we have a lot of freedom to fill in the probability assigned in each box, and the number is corresponded to the probability of the event corresponded to the box. So what kind of numbers can we fill in this gray box? It has to follow some restriction. So one restriction is the summation of each row should equal to this guy. Okay, so the whole board is called the join probability, and the green and the yellow and the blue one are called the marginal distribution of this joint distribution. So because this one is a marginal distribution, we have to follow the certain restriction, like the summation of the row is equal to the value on these blue boxes. And also for each of the column, the summation of the column should be equal to the number at the bottom in the that is right in the green. Okay, so that's the relation between the joint distribution and their marginal distribution. So let's go back to the definition. This means, okay, we try out all possible joint distribution that which has the marginal distribution that is already that we give right here and here. We see all kind of distribution like in this way. And we have to measure this value. That is the expected value of x minus 1. So it takes an absolute value or a norm, because our x1 might not be in the one-dimensional space. It might not just be a number. It can be a vector or any element in a element in a matrix space. So we can compute the distance between x and y. Okay, so back in our case, in this case, the expected value is pretty easy to compute, because if we put this A, B, C, D, E as 1, 2, 3, 4, 5, and if we consider distance between them in their numerical values, so the distance 5 minus 4 is equal to 1. 4 minus 2 is equal to 2. In that way, so we can actually compute this value. If we are consider A, B, C, D, E, we might not be able to do so because we don't know what A minus B is, or the distance between C and A. So if we put them in a numerical way, like 1, 2, 3, 4, 5. So A is equal to 1, B is equal to 2, 3, 4, 5. So we can compute the distance between the element or the event itself. Then we can compute this guy. Okay, so you know that in the diagonal here, the distance is 0 because okay, I put it into a wrong way. So if we put it in this way, so if I wish to this one to 0 and this one to 0, so this one is this one is 1 and this one should be 1. So I have to reverse the direction of the x-axis, and this one is 1, 2, 3, 4, 5. So I probably should put in the reverse order, but anyway, the only thing that matter is this guy and this guy is the same. Okay, so you can see that in the diagonal here, it's actually a good place to put number in because their cost is 0. That is, x minus y is 0. And the yellow lines, their cost is 1 because they are only have one differences, 2 and 1, and so on. And the red one has a cost as 2. So recall that we have some restrictions that so the summation of each row is should equal to this guy, and the summation of each column should equal to the green guys. Now we have a target or objective, of course under those restrictions, but we have an objective. We need to put the number in that satisfies those restrictions, but the values times its cost should be minimized. So of course, if we can put everything in the diagonal, the cost is 0, then that's perfect. But if we cannot do so, let's just try to do some arrangement so that the cost is minimized. So in fact, there are some easy way to imagine or solve the problem pretty easy for some easier case. For example, let's just see you have a lot of boxes. Say you have 15 boxes put together. So this one we have 5 boxes here, and 5 boxes here, and 5 boxes here. If we want to move this configuration into another one, like this one, and we try to do this in a minimal effort way. So what is the way to do so, to move this configuration into this one? So first of all, how do we actually measure the cost or the effort to move a box? We measure it in this way. So you can see that this box, if we move this box to this place, it moves 2 positions. So the cost is 2 because we move it by 2 positions. And for this one, we actually have 2 boxes. So the first one moves just to here, to 1 position. So the cost is 1. But we have to move 2 boxes, 1 here and 2 here. So the total cost for moving this guy to here, because we have 2 boxes and each of them, we are moving them 1 position. So the total cost is 2 for this part. And for the red part here, this guy, although we only have 1 box, but we move it, has the distance of moving it from 3 to 1, the distance is 2. So the cost is still 2. So right now we already have the cost of 4 already. And then the other way is symmetric, because we have to move these red guys to here in 2 positions. So the cost is 2. And 2 bucks, 1 position. So the cost is still 2. So the total cost is 8. 4 plus 4, or 2 plus 2 plus 2 plus 2. So this is exactly what the Western distance or Earth mover distance is. It asks what is the cost of changing one distribution into another. How much cost if we want to move one position, one distribution, and kind of adjust it to another. So what is the minimum cost? The minimum cost can be represent the distance between these 2 distributions. So this is why it also called the Earth mover distance, because if you imagine this one is not only just 15 bucks, it is like 10,000 small bucks, or just 10,000 dirts. So it is moving some earth from here to the other place. So that is pretty straightforward definition. That is, we measure the difference by the cost of changing it into another, from one shape, from one configuration into another. This one is not the only way to achieve the minimum cost There another way to do so by, we move this 3 to here. So the cost is 3, and move this 1 to here. And move this 1 to here, and 3 here. So 3 plus 1 plus 1 plus 3 is still 8. So there may be different way to achieve the minimal cost, but the minimal cost is a value that we can use as a measurement of the differences between these two things. So this is kind of like if you have heard about the edit distance between two strings, it's kind of similar. You edit one thing into another. So each operation has some cost. So what is the minimal cost? If they are exactly the same, then there's no cost at all. So the distance between a guide to a copy of itself is 0. But if they are different, so this is one way to measure the differences. So another useful scenario about the similar thing is we can actually use the same idea to measure the similarity between two shapes. So you can actually use it to query similar shapes in, say, a database or something. So we can actually use a tons of little dots to approximate a curve, like say 100 dots to approximate a curve. So each curve are approximated into 100 dots. Then we can ask if we want to move, because there are we don't know which one is which one, but there must be a way to move this guy into this guy. So what is the minimal cost? The cost can be measured in a distance. So what is the minimal total distance required to move this guy in to become this guy? So we can use this one to measure or to evaluate to get the similarity between two curves. Like what you do in calculus, we have infinite many dots. So that is a continuous version of this guy. So for Watson distance, basically we are working, in general, we are working in the continuous version. So how do we actually compute this guy? Do we have to consider all possible joint distribution? That is simply too many possibilities and too many things we need to optimize. So for example, in this guy, we actually we have 25 unknown variable need to be determined. So that is a huge solution space. So this seems to be very, if you think it is very difficult or complicated or very expensive to compute, you are probably right. So instead, we are using a dual form of this formula. So this one can be considered as a optimization problem because it has some restriction and we are trying to find the minima. And if you consider in this form, this one can be actually considered as a linear programming because it has to be satisfy some linear constraint, which is the summation of this row. These 5 variables should equal to 1/3, and the summation of all this guy has to be equal to this guy. And the object is also in a linear form. So in fact, this guy can be considered as a linear programming. There's a duality theory, so we know this linear programming has a dual linear programming. So the similar things happens to Watson distance, because you can actually consider Watson distance as a continuous version of the linear programming problem that we just presented. So it actually considers a dual form. The dual form is called the KR duality or Kontrowicz-Rubinstein duality. So the duality states like this one. We are considering the soup because it is in a dual form. Usually the dual form translate inf into a soup. So we have to consider the soup of this guy. So what is this guy? We are searching for different kind of function. So this function has to satisfy certain condition, which we call the Lipschitz condition. Also, we are going back to here later, but you know that the f is just a function, but satisfies some restriction. When given this function, what is the objective we are going to achieve? We are going to compute the expected value of f of x by using the first distribution, and we are going to compute the expected value of by using the second distribution, by using the second probability distribution. So the idea is to find an f so that the expected value for the first distribution is as different as possible to the expected value of the second distribution. So we are kind of like the total variation situation. We're trying to find an f that can emphasize the differences between these two distributions. But there's one thing we need to be very careful about it, is that if we find some f so that this guy has some differences, say the differences is equal to 0.1, just very small differences. So we replace this f by like 100 f to be our new f. So because the linearity of the expected value, now if we replace this guy as our new f, the value of this one is going to become 100 times 0.1, which is equal to 10. And what if we change this one to like 1000 f? Then this one becomes 1000 and this one becomes to 100. So you get a point that we can, if we don't have a restriction, any constraint over the f, we can scale up the f as large as possible so that the differences has no upper bound. So there's no maxima, there's no soup at all. So you see that we cannot, if we wish this definition to work, the f must have some restriction or constraint on its size. Okay, so this one is the constraint. So this one is called the Lipschitz. So you can see that it is kind of related to some norm of these functions, and it actually is. So the key idea of the Lipschitz function is that it does not enlarge the space. So especially when the k is equal to 1, we can just omit this one. So it means no matter what fx1 is or fx2 is, the differences between fx1 and fx2 should be equal or less or equal to their original distance. So you consider it as a mapping. It is going to shrink the distance between this input. So the distance between output is no larger than the distance between the input. So that's a restriction of the size. If f is continuous, f must be continuous. Let's say if f is differentiable, we can actually let x1 is converge to x2, and you will find that it is equivalent of saying if f is differentiable. If f is differentiable, it actually means f prime x is less or equal to 1. If x is multivariate, is a vector value or multivariate, it actually means the length of the gradient is less or equal to 1. Okay, so that's the KR duality. We have talked a lot of different things, but so far we haven't covered to why this is important and why this is related to gain. The thing is, this is our gain. So you can feel that f as a discriminator. So it is a discriminator. If we treat f as a discriminator, it actually kind of looks like gain, because this one is simply dx. X is from the real distribution, and we wish this one to be as large as possible. And when X is come from the fake distribution, that is generated distribution. If we are training the discriminator, we are hoping this one to be as small as possible. And of course, the generator itself have the opposite objective. Okay, so if we are trying to compute the Watson distance, we can actually use a gain-like architecture to compute this value. We simply wish to train this. We use our discriminator as our D, as our F. So this is pretty much the same procedure of training a gain. So that's why we are calling it a W gain, because we are start from something that is nothing related to gain. We are simply trying to compute the Watson distance, but finally, by using the KR duality, we see that, okay, we can use the gain procedure or the gain algorithm to in fact compute the Watson distance by using the KR duality. So that's the beauty and the idea of what W gain is. So the W gain is simply trying to implement this F as a neural network. But how do we actually do so? The question is, how do we actually find to force this neural network, the discriminator, to satisfy the Lipschitz condition? So one way to do so is to limit the parameters of this discriminator in a compact space, which we should say the compact space. So this means it's a compact space. So what is a compact space? It is a mathematical term in topology. Anything that is closed and bounded is a compact space, like a box. So if we put every parameter in the box, which means practically actually just means every parameter, say alpha ijk, something like alpha ij, is between, say, 1 and minus 1. And that's a box. We just put every parameter. So if we have 3 parameters, it's in a cube, but we have a really high dimensional parameter space, so it is actually in a hypercube. But no matter what, we should put everything in a range. So a mathematics theory states that if it is in everything is in a compact space, then it has a maximum. So if including your domain and your every parameter is in a compact space, then your Lipschitz norm is a finite. You have some k Lipschitz things. May not be one Lipschitz, but you have to be some k Lipschitz. And we don't actually care about what the k is, because we have already fixed our architecture of our neural networks. So there is some k. We don't need to worry about what k is, because we can actually divide the whole formula by k. We are trying to use k, f over k as our f in this formula. So this guy is less than 1. Okay, so that's one way to do so. But how do we force every parameter, every parameter in the weights of this neural network to be like bounded? So the W gain does something really straightforward or naive. That is, we clip the weight after each step of training. after the gradient descent, the back progression, propagation gradient descent or the atom, and then we simply cut out every, if alpha is greater than 1, say it is any value greater than 1, then we clip the value to make it to be 1. So we do something like alpha, if alpha is greater than 1, then we put alpha is equal to 1. So we clip out the value. So if alpha is less than -1, we do the similar thing. So that's with clipping. The authors of the double GAN realize it's clearly a terrible way. They know it's a terrible way, but it works. Okay, so we actually get something that satisfies the Lipschitz condition. However, the original formula requires to take the soup over all function, not just some function. But anyway, it kind of works. Okay, so is there a better way to do this Lipschitz contraction? If there is another way to enforce the Lipschitz condition without using this savage method. So one way to do that is another paper, the next paper of the double GAN, which uses the gradient penalty. Okay, so what we are trying to do is, so this one is the double GAN's loss function, and we add some penalty function so that the gradient should not be too big. So what is this x head? This x head is simply something between, so this one is the real data, and this one x bar is the generated data. We pick one pair of the real data and the generated data. We pick a straight line between them, and we randomly select one point on this line. So we get this x head. So that's the x head. So why picking this one? Because we know that we don't have to enforce the gradient, the Lipschitz on the whole domain. We only need to enforce this Lipschitz condition on the domain that we are caring about. So what is the domain that we are caring about? Obviously, anything near the true data is important. And since we have to kind of imagine our generated, this one is fake and this one is the real data. We're imagining that we are making the fake distribution closer and closer to the real distribution. So it seems to be fair enough to kind of clear the path between so we have to arrive from here to here somehow. So there has to be a path from here to here. So we have to kind of make sure in this path the Lipschitz condition is satisfied. But we actually don't know what kind of path is. We have no idea what the path is because it depends on how we train it. So we have no idea. So we just randomly pick one way to do so. That is the straight line between. So we just randomly pick one passable path because. So this one is x head and this one is the original, the true x. Because this one is as good as any. So we just pick this one. And this one works. That's how the double GAN with gradient penalty pick the x head. And another thing you need to observe is that if we are only forcing this guy to be less or equal to 1, so if we are trying to force it to less or equal to 1, why are there some penalties happens when this one is in fact less than or equal to 1? Say this one is in fact 0, which is very good. Then we still have, because 0 minus 1 square is equal to 1, so we got some penalty. As much penalty as when this guy is equal to 2, because 2 minus 1 is also equal to 1. So this one formula has pretty much no reason. This is because they are, by their experiment, it seems this one works better. There might be some explanation, but there's no solid theoretical reason about that. So anyway, this one is the default loss function. So we are only inspired by the mathematical formulas. We are not strictly following the mathematical formulas. So it actually shows that the W gain with gradient penalty is more robust and more stable than other kind of loss function existed like L scan, W gain with clipping, and this one, it doesn't really has much better qualities, but it is more stable in many settings. It is still not very easy to tune the meta parameters. What they mean is you have more freedom to choose the architectures of the networks. Okay, another extension of the W gain is Dragon, deep regret analytic generative adversarial networks. So it is also a very good paper and has a lot of insight, but we only take the one related to the W gain. That is the way it enforces the Lipschitz condition. It's pretty much like what the W gain with gradient penalty, except the X hat is chosen in this way, because the paper of Dragon observed that the X hat chosen by the W gain is still too wide, so it enforces the Lipschitz too much. As a result, it only chooses X near the real data. So this one is a small noise. So it only enforces the Lipschitz condition on real data plus some small noise, and it found out that it is quite enough. So we have some tutorials on W gain with gradient penalties, and you can also try in this repo. Another way to enforce the Lipschitz condition is using spectral normalization. This one is a demo of spectral normalization. So how does spectral normalization do? For most of the neural network architecture, it can be considered as a chain of linear and activations. So the activations are fixed functions, so there are no worries about the Lipschitz conditions, because they are just one function, there are no parameters on it. And for example, a common activation function is ReRu. The ReRu function. ReRu function certainly satisfies the Lipschitz condition because it looks like this one. So at this part, the derivative is simply 1. And at this part, the derivative is 0. So it is clearly bounded and less or equal to 1. So that's okay. Plus, they have no parameters. We can do nothing about it. So the only thing we need to worry about is the linear part. And if we can, if every linear part is Lipschitz, because of the chain rule, the whole function is also Lipschitz. So this one is actually more stricter than the Lipschitz because not only the whole function is Lipschitz, every component in this chain of functions composition is also Lipschitz. How do we actually make this one Lipschitz? If we translate the language of Lipschitz into a matrix and consider it as a linear mapping, a closely related concept is the spectrum of this linear function. The spectrum is defined in a way that it is the maxima of AH, the length of AH, divided by the length of H. So clearly you can see that this function can be considered as the spectrum, or if we call this the spectrum. So clearly you can see that this one is the constant of the Lipschitz condition for this linear function. So how do we actually compute this spectral value? It is kind of like the eigenvalue. You can use some iterated method to approximate this value. To compute the spectra is relatively expensive, but you can use iterated method to approximate it. So if A is a square matrix, the spectra is in fact the largest eigenvalue. So you can see that while it is relatively expensive to compute it directly, but can be easily approximated using iterated method. Okay, so similarly for even for a non-square matrix, we can approximate this spectrum very easily by using iterated method. So that's how we do. So we keep a record of the iterated result and get the spectrum for each matrix in this neural network. And we use the normalized version of W, which means the W over the spectrum as the new W that works in our neural networks. So effectively, our linear mapping, the linear mapping in the neural networks has spectrum 1. So this one is the algorithm. So it has some mathematics here and here to actually do the work. Keep a record of the spectrum for each iteration. In general, it only do one iteration in each training step because we are assuming that the W doesn't change much at each step of training. In the experiment, this is good enough to approximate the spectra. For the last part of our lecture, we're going to talk about some metrics that can evaluate the image qualities of the images generated by generative models. Because we are usually generate these images so that people can actually look at it. So the ultimate judgment is still made by human, by our eyes, objectively. These metrics may not exactly match the preference of human beings. It may not align with the preference of human beings. So for example, some of the models can achieve very high score in some of these metric, but still it can generate like 7 finger on one hand, or maybe some very strange pose of a human, or some building structures that is physically impossible. Our humans are very sensitive to these kind of things, like a slightly unusual human face, or like the number of fingers on a hand. You can imagine, although we haven't introduced this matrix yet, but you can imagine these metrics are not going to count the number of human fingers, and there are no mechanism of this matrix to actually evaluate the structure of the buildings. So yes, these matches are not perfect because they are not actually aligned with the human preferences. However, these matches are still very useful. Let me give you an example of why this matches is very useful. So for example, you are training like a lot of different iteration of the models. You have like 10 checkpoints. So how do you find out which checkpoint is the best one? Probably you have training it automatically. You wish it to automatically find out which one is the best. And how do you actually compare your models to other people's models? So sometimes you wish to compare your models with other guys, or you wish to compare your models with other models you trained by yourself. Although human eyes are the ultimate judgment, but we are very easily biased. People are tend to think the meal they cook by themselves is more delicious because they put some effort in it. So it is very difficult to compare your own models with other people's. So these metrics provide a way to do it more subjectively. Although they have their own weakness, but they can still be very useful and sort of um, fair in some sense. So let's look up what these metrics are. So let's look at the first one, the inception score. The inception score is based on a simple observation when we're doing the classification. So we are usually have a softmax at the end of a classification model, and we output some probabilities. Usually, when given a picture, because it is belong to some category, we usually have a very uneven distribution. So one of the category has a very high probability, like 0.9 or like 0.95 or even 99%. On the other hand, if an image is not in the dataset because it doesn't clearly has an object that is in the given categories, it may have a very even distribution because we don't know which category it is. So this makes some difference between the real image and something perhaps to be fake, or at least the quality is not so good. And the other observation is that if we consider all of the different categories together, so in this case you are considering about the CIVA10 or MNIST, usually each category in the training data has an even distribution because we have like 10% for the MNIST, we have 10% digits are 0, 10% are 1, 10% are 2. So for if a model is generating a distribution that is like the original dataset, so for the all dataset, not just for one image, for the all dataset together, the accumulated distribution should be pretty even. That's the basic idea of the inception score. We're comparing the distribution on a single images with similar, especially where with similar labels, they should have the high percentages together. So that's a basic idea of inception score. We're considering the accumulated distribution of one category, and we are consider the accumulated distribution of all categories together. In the left hand side, it should has some distribution that is very uneven. And on the right hand side that we consider all category, it should have a very even. So the inception score compares the differences between this, the left distribution and the right distribution. And if they are very different, it will have a very high inception score. So that's the inception score. So it compares the difference using the K divergence. And we are doing some mathematics here so we can have a more interpretable score. However, there are some very interesting properties of this score. So for example, it is possible to actually optimize over inception score and get perfect score. So these two images are getting perfect score on inception score. The first one is directly optimized towards the inception score. So you can see that it generates totally random, still like a noise like images, but it can get nearly perfect inception score. So can we actually kind of cheat, but not so obviously? So one way to do that is we train a model first in a more normal way. Then we kind of fine tune this model towards the inception score. The second one is doing exactly the same method to do so. So it first train a model that can generate uh, normally on CFR10, and then it fine tune it towards the inception score. So that's still, I mean, the image quality is definitely getting worse, but the inception score is getting better. So let's give us a very important lessons. If we wish this score or matrix to be useful, we should not attempt train our models towards this score. Another important, more modern matrix is FID, Frechet inception distance. So this one is a distance, not a score. So for score, the higher is better. For distance, lower is better. So it is based on the Frechet distance. This is a distance that kind of similar to the Watson distance. It compares the difference between two distributions. So you can see this one is the definition of the Frechet distance. So for the multivariate Gaussian distribution, we can actually, there's actually a paper in 1982 to derive the formula that compute the FID between two multivariate normal distribution. This one on the top. So we only need the mean and the sigma of these two normal distribution. So what is the FID, Frechet inception distance? First, we feed the images into a function. The function is in fact a model, an inception V3 model trained on ImageNet. So okay, we have F that is an inception V3 model trained on ImageNet. So we give the images. So like we have so for a standard way to have 50,000 images. This 50,000 image, we have a set of 50,000 images that is taken from the training dataset, and we have another 50,000 images that are generated by our model. Our goal is to compare the difference between this distribution for the first set and the second set. Okay, so for each set, we have 50,000 images. We are sending it into the F, that is the inception V3 model. So after the forward process, we got our hidden states of the hidden layers. You can consider the hidden layers is a very huge factor. It has a lot of dimension components. We flatten it. So because we have 50,000 images, so we can actually compute the sample mean of each component. And we can compute the sample covariance between each pair of the components. We are just using the mean and the sigma, and compute the Frechet distance as if they are normal distribution. So that's how we compute the FID. Compared to inception score, FID is more straightforward way to calculate the score because it does not depend on a classifier. For inception score to work, we need to generate images that is compatible with the categories of the classifier. However, FIT can be used for any kind of image, so that is more convenient. The last method we are going to introduce is the precision recall method. Precision and recall are very commonly used in many fields like object detection and a lot of defect detections. So how does this precision and recall idea apply to evaluate the image qualities? Well, actually consider two manifolds. Manifold is a terminology in mathematics to describe the surface space in higher dimension. But in this context, you can simply consider it as a set, just a collection of things. But these things are continuous linked together, not discrete points over space. It is connected. You are simply consider a connected set. That's fine. But we are still going to use the terminology manifold because it is the word used in this paper. Okay, so let's consider two manifold. One is the real manifold. Imagine we already has that. So every real image is on this manifold. And the other is the generated manifold. So every generated images is on this manifold. Although we don't actually have the blue one, the real one, because if we already know how to judge an image is on this real manifold. So after we have generated some images, we can simply reject images that or discard this image that is not real enough. So we don't actually have this blue manifold. But just first imagine we have such a manifold. So how do we compute the precision and the recall? Then suppose we already have this manifold, then the computation of precision recall is quite straightforward. For the precision, we're considering how many percentage of the intersection of PR and PG over all PG. We call this the intersection the true positive. We are considering the red one predict positive or generated positive. We can say that. But by using the terminology of precision recall, we call the red one the predict positive. And the blue one is we simply call it positive. So by computing the precision, we are going to measure how many generated images are in fact real. So we are computing the percentage of the true positive over all predict positive. On the other hand, the recall, the metric recall means how many positive images, how many real images can be actually generated by our model. So we are calculating the percentage of the true positive over all positive samples. So that's it. So one is precision and the other is recall. You can see both these two images to illustrate the meaning of these two concepts. So it left us only one issue, which is a big issue. We don't actually know what is positive. We don't know how to judge which image is real or not. If we know how to judge an image is real or not, we don't even need a discriminator. We need a discriminator in the first place is because we don't know how to judge which image is real or fake. So how do we actually implement this metric? It uses a simple and naive but inaccurate way to approximate the true manifold. So the way it does is, okay, we have a lot of different samples in our dataset. Then the way that we judge an image, whether an image is real or not, is by trying to finding an image in a dataset that is very close to these images. So how close is close enough? So let's look at this formula that defines the approximate manifold. So we have a data set right here, and this guy phi is the image that we wish to determine whether it is on the real manifold or not. So first, for every single images phi prime in the data set. So the whole inequality says that, okay, if we are putting this phi into the data set, then this phi is among the k nearest neighbor to phi prime. So that means phi is close or near enough to phi prime. So if phi, this whole formula means that if phi is near enough to any of the images in the dataset, then we are consider phi to be on the manifold. Okay, so you can see that's the visualization of this approximate manifold. We are simply putting a bunch of disks around each of sample. So you can see that this approximation is definitely very simple, naive, and if we actually use this f as our discriminator, you can imagine that our generator, it can only produce something like images that is very near to the true sample in the dataset. This is not a very good approximation. However, the result of this paper is saying that although this approximation is very lousy, but the result precision and the recall score is good and kind of align with what people are actually perceive for the image quality. So that's how they define the precision recall. That's just one way of defining the precision recall, but this definition is used in the evaluation like FQVA or big N. So that's the definition of this precision recall formula. And you can actually use in the similar way to define a realism score, like this one. And sort of echo to what I was saying, why not just reject all images that is not real? People are actually doing so. So if we define a realism score like this one, you can actually generate a lot of different images by using your method, like 4 images and 10 images, and pick the one with highest score so that you can increase the fidelity of your images, but sacrifice the diversity of the images. So, but that's a way that if you are in favor of fidelities over diversities, so that's one method you can use to improve the qualities by sacrificing the diversity. Okay, so that's all for today's lecture.